Welcome to This Explainer. Today, we're diving straight into the invisible engine that drives absolutely everything in our world. And I mean everything. From the deep biology happening inside your own cells right now, to the cutting-edge tech powering the electric vehicle revolution, there's this one fundamental mechanism at play. It's essentially a universe-wide accounting system. And once you understand how it works, you literally unlock the secrets to how energy is transformed everywhere around us.
So take a second and think about this. What do a massive rusting ship sitting in the ocean, the smartphone in your pocket, and a giant oak tree growing outside actually have in common? On the surface, absolutely nothing, right? But if we zoom into the microscopic level, they are all intimately connected by a single, incredibly simple transaction. They're all driven by the continuous swapping of electrons.
In chemistry, we call this process redox, which is just short for reduction oxidation. Modern chemistry defines redox strictly by this simultaneous transfer of electrons. And because of the law of conservation of charge, you can't just have one without the other. These reactions never happen alone. It's like a cosmic mirror. If one substance loses electrons, another substance absolutely must gain them in that exact moment. A classic foolproof way to remember this is the old mnemonic oil rig. Oxidation is losing electrons and reduction is gaining electrons. If you can keep oil rig in your head, you've pretty much got the master key to everything we're going to talk about today.
Okay, let's lay out our roadmap. We'll start with part 1, the oxidation number electron ledger. Then part 2, batteries. Part 3, smelting. Part 4, corrosion. And finally part 5, the metabolic cycle.
Let's jump into section 1, oxidation number, the electron ledger.
To keep track of this wild, invisible economy, chemists use oxidation numbers. It's basically a strict financial ledger, assigning ownership of electrons in any compound. But here's the catch. Electrons aren't shared equally. It's all based on electronegativity, which creates a really rigid hierarchy. Look at these priority rules. Fluorine is the absolute king here. It's the most electronegative element, meaning it always takes the electron and gets a -1 charge. Always. Now down in 4th place is oxygen. Oxygen is normally incredibly greedy and usually takes a -2 charge. But if you force it into a molecule with fluorine, oxygen actually gets bullied into giving up its electrons. So this hierarchy is absolutely crucial because it keeps the thermodynamic ledger perfectly balanced. It dictates exactly who gets oxidized and who gets reduced. And that brings us to this microscopic tug-of-war. Depending on who's winning, substances act as either oxidizing agents or reducing agents. And you have to pay close attention here because it sounds a bit counterintuitive at first. Notice how an oxidizing agent is the aggressive one. It steals electrons from others. But by gaining those stolen electrons, the agent itself gets reduced. On the flip side, a reducing agent generously gives its electrons away, meaning it loses electrons and therefore gets oxidized itself. It is a perfectly balanced, totally dynamic relationship. Things like oxygen and chlorine are your classic electron thieves, while metals like sodium and magnesium are just super eager to give theirs away. We can actually rank this eagerness to give away electrons using the ionization tendency series. Take a look at the far left: potassium, calcium, sodium. These metals are incredibly strong reducing agents. They are basically desperate to give away their electrons and dissolve into ions. But follow that all the way to the right side, to gold and platinum. Gold fiercely hoards its electrons. It absolutely refuses to be oxidized, which, by the way, is exactly why gold jewelry stays shining for thousands of years without tarnishing. So now that we know the basic rules of the game, let's see how human engineering actually harness this thermodynamic power.
Moving right along to section 2, batteries, taming the electron.
So by physically separating the oxidation and reduction reactions and forcing the electrons to travel through a wire to get from one side to the other, humans created the battery. But what's really fascinating here is the concept of dynamic polarity. We usually just think of a battery as having a fixed positive and fixed negative side, right? But scientifically, the anode, which is where oxidation happens, and the cathode, where reduction happens, actually swap identities. When you're using your phone and discharging the battery, the negative electrode is the anode, giving off electrons. But the second you plug your phone into the wall, you force that current backward. Suddenly, that exact same negative electrode is receiving electrons, instantly turning it into the cathode.
In modern lithium-ion batteries, this whole process is stunningly elegant. It relies on a process called intercalation. Instead of completely dissolving huge metal plates like in older batteries, tiny lithium ions smoothly slip in and out of the molecular layers of the battery. Think of it like books just sliding neatly onto a shelf. You force them over to the anode during charging, and when you turn your device on, they naturally just want to flow right back to the cathode. As they do, they push electrons through your device to power it. It's a brilliant system, though as you might have heard, researchers are actively trying to shift away from flammable liquid electrolytes towards solid-state batteries to prevent thermal runaway and make the whole thing safer and even more efficient.
Let's look at Section 3, the backbone of industry, smelting.
So let's zoom out from the micro scale of batteries to the massive scale of human infrastructure. Think about heavy industry, like a giant blast furnace. Nature very rarely gives us pure metal. It prefers to give us iron ore, which is just iron tightly bonded to oxygen. To build our modern world, our skyscrapers and bridges, we have to physically tear that oxygen away. So inside a blast furnace at over 1,000 degrees Celsius, we introduce carbon monoxide. Carbon monoxide is an incredibly powerful reducing agent. It acts as the ultimate electron donor, aggressively stealing those oxygen atoms away from the iron ore to create carbon dioxide. What's left behind is pure molten liquid iron. That single redox reaction is literally the foundation of the modern steel age. But what about metals like copper, where we absolutely need 99.99% purity for things like electrical wiring? For that, we use electrorefining. We actually use electricity to force raw copper to oxidize, dissolving it into a liquid bath. And then we cleanly reduce it onto a pure plate. But here's the crazy part. That raw copper usually contains impurities, including valuable stuff like gold and silver. And because of that ionization tendency we talked about earlier, gold and silver refuse to oxidize. So while the copper dissolves, these precious metals just sink to the bottom of the tank as this dark mud that the industry actually calls anode slime. Refineries scoop up this slime and extract massive amounts of highly profitable gold and silver from it, all thanks to the strict, unbreakable rules of redox. Next up is Section 4, Corrosion and Defense, the Invisible War. Of course, thermodynamics is a massive double-edged sword. Take a look at this number, negative 0.44 volts. That is iron's standard reduction potential. In plain English, it means that iron naturally wants to oxidize and surrender its electrons the moment it's exposed to the elements. Literally, a single droplet of water resting on a massive steel bridge acts as a devastating microgalvanic cell. The iron gives up its electrons, dissolving into the water, while those same electrons travel to the edge of the droplet to reduce oxygen. They combine to form iron oxide, rust. It is a relentless, invisible war that is constantly, slowly devouring our greatest engineering marvels.
So how do we fight back? Well, engineers actually use redox against itself, which brilliantly illustrates the power of understanding this chemistry. To protect ships and underground pipes, we often attach heavy blocks of zinc to them. Since zinc is a stronger reducing agent than iron, it willingly gives up its electrons first. It literally sacrifices itself, eroding away completely so the iron doesn't have to. Hence the great name, sacrificial anode. But for something truly massive, like a cross-country oil pipeline, you can't just use blocks of zinc. Instead, we use ICCP, or Impressed Current Cathodic Protection. We hook up a power source to pump an endless, continuous supply of direct current electrons straight into the pipeline. By artificially flooding the iron with all these extra electrons, we completely stall its desire to oxidize, essentially rendering it immune to rust. Finally, Section 5, the breath of life, the metabolic cycle.
Redox isn't just about heavy metals and machines, it is the engine of all life on Earth. If we trace the biological energy flow on this timeline, it starts with photosynthesis. Plants use the intense energy of solar photons to brutally oxidize water, tearing its electrons away and releasing oxygen into the atmosphere. They then use those harvested electrons to reduce carbon dioxide, cleverly locking the sun's energy into the highly stable chemical bonds of glucose. Then you eat that glucose. Through a process called cellular respiration, your mitochondria oxidize that glucose, ripping the electrons right back out, step by step, to extract ATP. That's the energy currency that powers your muscles, fires your brain, and literally keeps your heart beating.
But here's the catch. Those depleted, exhausted electrons at the very end of your metabolic chain, they have to go somewhere. They desperately need a final destination. Enter oxygen. The oxygen you are breathing into your lungs right this very second serves one fundamental purpose in your body. It is the ultimate, ruthless electron acceptor. Because of its massive electronegativity, it happily catches those depleted electrons at the very end of cellular respiration, combining with hydrogen to safely form water. If you didn't have oxygen there to catch those electrons, the entire biological redox chain would back up and stop instantly. So, from the rusting of a massive steel bridge to the battery inside your phone,
all the way down to the oxygen filling your lungs, it all comes down to the microscopic swapping of electrons. And as we look to the future, mastering these quantum electron swaps, whether that's by building better solid-state batteries or engineering brand new green tech, is the absolute key to global carbon neutrality and our overall technological survival. It truly is the master ledger of the universe, and we are really just beginning to learn how to read it. Thank you so much for joining me on this explainer. The next time you take a deep breath of air or plug in your phone, ask yourself, what other invisible ledgers are quietly dictating the absolute limits of our reality?